experts in the subject, like chiral symmetry restoration, deconfinement, also the transition to the quarkionic phase, etc. So this is, okay, forget it. I mean, you know that better than me. This is the general scenario. Here I added also the possibility of having a isospin chemical potential dependence. But it's an extremely rich phase diagram that's worthwhile to be analyzed, of course. Now, today I will speak about electric fields. This is a scenario that appears when you have collisions between different nuclei. I mean, a quite heavy nuclei like gold or lead colliding with a small nuclei like copper. Then you have a strong difference in the number of protons that participates in the collisions. And therefore, due to the imbalance of the charge, a strong electric field appears, precisely because you have here much less protons than here. And the interesting thing is that this electric field is a kind of dipole electric fields perpendicular to the magnetic fields that points perpendicular to the collision plane. The electric field is along the collision plane. Now this, many of you know this transparency. I took it from this paper by Rogaszewski et al. They did a simulation how this electric field appears precisely in collisions. I don't know, I think it's gold, copper, or something like that. And you see here, well, I cannot see nothing, but these red lines and blue lines denote the electric fields in the collision plane. The magnetic field is perpendicular, yeah, copper, gold. And this is the evolution in time of the magnetic field that appears and the electric field. So the electric field is important. It's not negligible. And it appears in this collision of different type of nuclei. Yes? Okay. Now let us go into our job. Our job today is to discuss the behavior of pi-pi scattering lengths. How these experiments are doing or were done, I will mention later. But this is the general structure. If you have pi-pi scattering, then you will have a dependence on the isospin numbers. Each pion can have a isospin 1, 0, -1 set component, of course. And this is the general structure from quantum mechanics. This is in the S channel, T channel, U channel. And there's, in general, you have to summarize all possible combination in a symmetric way of the isospin indexes. These are projectors that project into isospin 0, isospin 1, isospin 2. Sorry, I did it wrong. Okay, and in this way, you find the projected scattering amplitudes into well-defined isospin channels. This is isospin channel 0, 1, and 2. And when we speak about pi-pi scattering lengths, we refer always being inside the elastic regime. I mean, without going into the threshold where you start producing pairs of other pions. These are standard reference, beautiful reference about this formalism. Now, in general, and this is a matter of a quantum mechanics book, every scattering amplitude can be expanded in a series of partial wave amplitudes with defined angular momentum. And when you are close to the threshold, these scattering amplitudes behave in this way. And here is where our hero appears, this scattering length, close by to the threshold. And in fact, you can expand this thing around the 4m pi, and you get this expression for the real part of this partial wave amplitude. And the scattering lengths are defined as this limit. Scattering lengths refer to the highly non-perturbative regime, very low energy. And this definition can be extended to other angular momentum channels. In general, this is the definition. And there is an order. This is a hierarchy between the different scattering lengths. Certainly, the one that dominates is the scattering length for zero angular momentum here, A0. And well, at very low energy, everything is dominated by this channel. And there is a beautiful result, old result by André Martin, an inequality between the different scattering lengths. Well, but this is just, sorry, I did a mistake. Well, pi scattering lengths and all this stuff appear in the old good times of starting nuclear physics, where people studied scattering of pions with nuclei and proton-proton. If you look at the book on nuclear physics, you will see that the discussion is always referred to this language of scattering lengths. How scattering lengths were measured in particle physics. I mean, you cannot send a beam of pions against a beam of pions. This experiment is not possible. Scattering lengths were measured among the pions that appear, for example, in the decay of K+. K+ decay, pi+, pi-, positron, neutrino. And people were able to discuss the distribution of these pi+, pi- pairs, discovering that there was a scattering among these particles. The first experiment was done by Laurent Rosselet, 1977. There is more new experiments. The Dirac experiments, they produce pionium atoms, so an unstable system of a bound state of pi+, pi- that annihilates later, of course, and they were able to measure wonderful measurements for this difference of things. And more recently, well, this is the stuff about pionium atoms. And more recently, Eppelbaum and these two gentlemen studied also pi scattering lengths in the decay of heavy charmonium states like psi prime, for example, and you have it here. Sorry. Okay, here you have the decay of psi prime into the normal J psi plus pi 0, pi 0, but in the meantime, there is an intermediate region where you have these processes that can appear where scattering among the intermediate pion states have been measured. And in fact, this is the result. That is the distribution of the number of pairs of pions as function of the invariant mass of the pi 0, pi 0 system. And you see clearly the appearance of a cusp here. That is exactly, at the point where the pi scattering lengths take place. So these are the measurements. Now let us go into our stuff. I will explore the behavior of pi scattering lengths in the frame of the linear sigma model. You know this sigma model pretty well. Well, here you have it. We will only concentrate on bosonic degrees of freedoms. The fermions here are nuclei, are protons, neutrons, extremely heavy states. And we have already shifted the sigma vacuum, the sigma field around the expectation value. And that's the model, okay? It has is SU2 cross SU2 symmetry, which is explicitly broken by this term. And it's a wonderful model. We have used it many, many times in different physical scenarios. Okay. Now, well, the model gives you every mass are given in terms of the vacuum expectation value of the sigma field, which is called V here. This is a well-known relation. And at the tree level, you can compute the different scattering lengths, the different scattering amplitudes. Here you have it. Isospin 0, isospin 1, isospin 2. And in fact, the model works pretty well. Here, these are experimental results from the previous experiments I already mentioned. These are the prediction for Chiral perturbation Sion, and you see that the linear sigma model is doing pretty well. I mean, these are for different quantities, okay? Well, now we will compute the effects of electric fields and homogeneous electric fields. Later, probably Enrique Muñoz will talk to you about producing some fluctuations around, but this calculation was done for an homogeneous, constant electric field. Highly, well, it's not evident that this is the real physical scenario, but nevertheless, this is what we did. This is the Schwinger propagator for electric fields. You have it there. And now for our calculations, we went into the regime of electric fields of small intensity. So we expanded the previous propagator, and you find this propagator for in the regime of small electric intensities. Okay. Now, these are the diagrams we computed. In the S channel and in the T channel, the dotted lines denote, or dashed lines denote the propagators for sigma fields, and the continuum lines are the propagators for pions, yes, charged pions. These are not fermions, and there are no fermions in this game. We compute all these diagrams, and for the first time in this paper, we computed with full detail the box diagrams, which are this one. These box diagrams are, of course, small. They contribute very little to the calculation, but because the mass of the sigma, which is about 550 MeV, is pretty high compared with the mass of the pions. But for other reasons, we decided to calculate it. I mean, now the calculation is complete. And these are the results. And it turns out that we find projections, scattering amplitudes only at the 0 isospin channel and isospin channel equal 2. There are no projection into the channel isospin 1. These are the results, okay? It is what it is. And as I said, I emphasize this because the box diagrams are naughty diagrams, are quite difficult to calculate, yes? And we will, if you are interested, you will find all technical details in the reference I mentioned. Okay, and this is the result. You see there is a huge effect of the scattering. The blue one is the scattering length in the isospin 2 channel compared with the small, well, increasing behavior in the isospin 0 channel. This as function, I don't know if you see, as QE, the intensity of the electric field divided by, normalized by the square of the pion mass. I forgot here, sorry, I realized today when I was checking everything that I forgot to mention that lambda was taking us 4.26, which is the normal value of lambda in all type of calculations. Okay. And this is totally different with the behavior of pi-pi scattering lengths when you have magnetic fields. When you have magnetic fields, we found that the normalized scattering lengths, the blue one now is the A02. This increase, and the other one decreases a little bit, but the magnitude of increasing is much smaller than in the case of having electric fields. Now, in the past, we also studied the effects of magnetic fields together with temperature effects in this article. And more in the past, we had papers with Alfredo Raya and other students, and also Enrique, where we studied the effects of only in these previous papers temperature, and now we took into account magnetic field intensities. This is interesting because when you take into account simultaneously temperature and magnetic field, you see that there is a competition between these two effects. They conspire against each other. So it will be very difficult to disentangle effects of magnetic fields and temperature I think in many experiments, yes? So this thing of handling now electric fields open an interesting window. In general, as I said, there is an agreement that it will be extremely difficult to disentangle magnetic from thermal, sorry, oh, what a mistake, yeah. Okay, therefore, I was very impressed about the talk by Alejandro about the seed decays into pairs of muons, because this opens really a window to see if you can say something about magnetic effects when temperature is already there. So collisions between asymmetric nuclei due to the important role of the electric field might be an interesting window for exploring this kind of physics. Yes, okay. Now let me go into the second topic, which I call something else. I was afraid about the reaction of Anna Julia because probably she would have kicked me out from the conference because there you will see non-reference at all to electromagnetic fields. It is something totally different. We uploaded this preprint to the archive, as I said 2 weeks ago. This refers to the thermal behavior of Regge amplitudes, which is an old stuff in strong physics. Okay, in general, we say that an amplitude becomes Reggeized when it has an analytical behavior in angular momentum, and in the high energy limit, it is when the S variable, Mendelssohn variable, goes to infinity, staying T finite, then you find this kind of behavior. And we say that alpha of T is the trajectory of this amplitude. And this happens when resummation of diagrams are considered. You can see, for example, this in the book by Collins, an old book, but a fantastic book actually, Introduction to Regge Theory and High Energy Physics, okay? Let us continue. Well, let me present you the kind of things people have done. We will play around with the lambda phi to the cube model. And let us consider this model, and we will focus on these ladder diagrams, yes? And the building block for such ladder diagram is precisely this box diagram, okay? You can calculate this box diagram. And it can be shown, I didn't put all technical details because the calculation is pretty long because it is a box diagram. You can show that in the high energy limit, this box diagram has this behavior. It emerges a log S divided by S, where K of T is this expression, okay? Now you have to consider the N ranks, ladder diagrams with N ranks, and then of course the expression for this N ranks diagram, which was this diagram, has of course this expression. And now you have to sum from N to 0 to infinity, and this is the resummation I mentioned before. And it turns, that's what I mentioned, the amplitude of S and T. The small t denotes the Mendelssohn variable. And well, you get this expression, which is precisely of a Reggeized type of amplitude. In the old times, in the 60s, there were fantastic calculations by Gelman and collaborators and Cheng and collaborators in the frame of QED, analyzing if particles were real, elementary in the sense of having a pole in a scattering amplitude or being Regis particles. Well, here we identify the rigid trajectory here, alpha of t, in terms of the variable k of t, of the function k of t I mentioned before. Now you may expand this. Now we repeated the calculation with temperature effects. Now you compute everything, keeping in mind that now having temperature, when you have an integral over d4q, the q0 becomes a sum over Matsubara frequencies, and bosonic frequencies, and then you have this thing. And you first calculate the box diagram. The result can be decomposed in this way after playing with Feynman tricks. This is a pretty long calculation. It sounds very trivial, but it's not trivial at all. And it can be decomposed as a zero temperature contribution plus a finite temperature contribution. These are the expressions. Here you have temperature. And now you have to play with the Feynman variables. And it's possible to show that the temperature-dependent contribution has this expression. Details are in the article, of course, in terms of this function of t and beta. T is the Mandelstam variable, and beta is 1 over temperature. And you insert this temperature independent part and sum the temperature-dependent contribution, and you sum over the all infinity ladder, and you find effectively that you have a Regis scattering amplitude that depends now on temperature. And the phenomenological effects are interesting. I'm coming close. I am close to my end. You expand it for small values of t, and then you get a linear rigid trajectory, where alpha of t, oh, sorry, it should be alpha prime. Yeah, sorry, I apologize. Well, this is completely alpha of t. And alpha 0 is the part that is not dependent on temperature, yes. Well, now we did something very bizarre. Well, we said, okay, we will put this result into the old Chiu-Frauchi rigid trajectories. This is physics of the 60s. You know, particles can be classified also as be members of different rigid trajectories. This is the rigid trajectory of the Rho meson, A2G, A2. They are incredible. The particles are organized in rigid trajectories also, linear rigid trajectories. So we said, okay, let us take our result and use the Rho rigid trajectory and use the values of the intercept here, 0.5 for the Rho and 0.9 for the slope, and see what happens with our results. And it turns out that the slope of the rigid trajectory becomes smaller. It decreases a little bit as function of temperature. And this happens also for other rigid trajectories. For the pi, if we parameterize in terms of the parameters of the pion rigid trajectory, you see that the slope becomes smaller. This means that the mass becomes bigger as function of temperature because the angular momentum cannot change. Angular momentum has to, here is angular momentum, of course, and here is the invariant mass. Angular momentum has to do with the Lorentz group, so forget it. But what can change here is the mass, because if you have angular momentum 1, as is the case of the Rho meson, you have to move a little bit further to the right and you see that the mass increases. And in fact, if you do this calculation varying temperature, you will find that this is the evolution of the Rho mass as function of temperature, just because the slope of the rigid trajectory diminishes. the slope becomes smaller. And it's amazing that this behavior is quite similar to a calculation we did many years ago with Cesario Dominguez and Cristobal. This was the reference, SAIFR 56. Many of you were not even born, probably. 93, SAIFR 56C. This is our, well, look, the scales are different, so it's difficult to compare. This is a very small scale, little scale here. And here I present the results in terms of temperature. Here you cannot see it, is presented in terms of the normalized temperature. But anyhow, you see that the result is quite similar. Also, we compare it with another result for mass evolution. We did with Renato as function of temperature. And this calculation was done in the frame of unitary arguments and the virial expansion using results from pi scattering lengths in kaon decays. Totally different arguments, and nevertheless, the behavior of the mass as function of temperature is interestingly similar. So something true must be behind things I have said. The interesting point is that the slope of the rigid trajectory diminishes as function of temperature. So my conclusion is the following. It doesn't work at all, but it doesn't matter. My conclusion is a very stupid conclusion, is that it's always interesting to have new perspectives for old results, because this opens new windows. I don't know if this will work. Oh, it is a kind of conclusion. I never like to put conclusions, because in my opinion there are no conclusions, there are always open questions, but nevertheless, new approaches as handling the rigid thermal contributions to rigid trajectories may be interesting, because this opens new perspectives to old problems. Yes, okay. Okay, thank you so much. This was.
We have time for only one question, but today we have a longer discussion session also for the talks of yesterday.
I have a very simple question about temperature dependence of rigid trajectories.
Yes.
Heat bath breaks Lorentz invariance, so there is a fixed frame associated with the heat bath. And when you do resummation of boxes, it corresponds to ordering of these boxes in rapidity. So all of these boxes have different momentum relative to the heat bath. So it appears that this should spoil the resummation, because different boxes are at different momentum relative to the heat bath. Is it taken into account?
There is a hierarchy I forgot to mention here. The S variables must be definitely much bigger than temperature and bigger than the T Mendelssohn variable. It's in this frame where these results appear. And also, our result was for small range of temperatures. We expanded for small value. If you take for high values of temperature, then things become not so clear, probably because what you are saying. So I don't know if I can go back. So let me see here. Okay, here. There is a, we expanded this. And this result is, you see, it's an expansion in terms of powers of beta, and beta is 1 over temperature. So this is an expansion of our results for small values of temperature. And we move with temperature in a range. This is the, you see, temperature 0, 40, 50 MeV, and we stop there, because this is temperature related, in this case, to the mass scale of the problem. If you go to higher temperature, probably you are right. Yes?
Sorry, we don't have time. Let us thank Marcelo again. And yes, as I said, the discussion session today will be longer, so you have the opportunity to ask more questions to the speakers of yesterday, because yesterday we had to skip the discussion session. And something else, you probably saw the program about sessions, so people have been asking me, what is this? So most of you don't have to be here. It's a session to decide future editions of this conference, and only the people from the International Advisory Committee will be present. So you will have lunch, don't worry, okay?
Hello, can you hear me? Oh yeah, great. Great. Oh, you have to carry it over.
Enrique?
Okay, thank you, Enrique. So, good morning. First of all, I would like to thank the organizers, Ana Julia and Giorgio, for this kind invitation to present my work at this nice workshop. And the work I will present today is a collaboration with Jorge Castaño, who was until recently a postdoc in my group. Now he moved for an independent permanent position at Universidad del Valle. And my colleagues from Chile, Marcelo Loewe and Juan Cristóbal Rojas. So the motivation of this work is starting in the heavy ion collision scenario. So due to the charged nucleons that participate in the collision, we can picture the situation as two opposing classical currents that will generate within the region of the collision a very strong magnetic field. And all the simulations, including hydrodynamic simulations, indicate that these magnetic fields could be as large as 10 to the 19 Gauss, roughly speaking. I mean, a few times the pion mass squared. But not only they are very intense at the initial stages of the collision, but they are also inhomogeneous according to most simulations. And these inhomogeneities, they can be pictured not necessarily as deterministic inhomogeneities, but also since we have in this collision scenario different initial conditions prior to thermalization, then an alternative picture for this is to imagine that these inhomogeneities are originate from stochastic fluctuations in those currents. So in general, most theoretical work based on the analysis of heavy ion collision scenario phenomenology in magnetic fields assume for technical reasons that the magnetic field, due to this classical background, is uniform and constant in time. All this work goes back to the seminal work of Schwinger, of course, with his propagator, which is based, again, on this simplifying assumption. Here, trying to go one step further in this direction, we propose a statistical model to take into account such inhomogeneities as stochastic effects. Okay, so it's not going the right way. This way? No, it's one. Okay, so this is the Schwinger propagator for the case of a constant magnetic field. In this case, the magnetic field imposes a preferred direction that breaks the Lorentz invariance into two orthogonal subspaces, as you can see, of course, in the metric, the parallel and perpendicular components with respect to the magnetic field. And the Schwinger propagator can be expressed in terms of a translational invariant part, which is this expression that can be written in terms of a Schwinger parameter integral, and also a gauge dependent phase that guarantees the gauge covariance of the propagator. This is called the Schwinger phase. It involves a line integral of the gauge field. This is the classical gauge field that determines the magnetic field. And there is also contribution from the tensor, electromagnetic tensor, that if we choose a straight line connecting these 2 points, this term by antisymmetry of the tensor will vanish. So this propagator can be parameterized alternatively by using the same Schwinger representation in terms of a single scalar integral, which is this A1 expression. we proposed this particular parameterization in this article back in 2023, according to this work. And this single scalar integral can be expressed as in terms of Landau levels. So this is the lowest Landau level contribution plus all the other higher order Landau levels. And the other coefficients, as you may see, A2 and A3, that determine the rest of the tensor structure of the propagator, are determined in terms of derivatives of A1 with respect to the K-perp component of the momentum, same as with A3. So everything gets parameterized in terms of this A1 function in this nice enclosed expression for the inverse propagator. So now, how we try to go further and implement these stochastic fluctuations in the magnetic field? The basic picture is that we have these classical electric currents, which are given by the charged nuclei that participate in the collision. And since we have, in principle, random initial conditions, these classical currents will have, from a statistical point of view, a fluctuating component. So this is basically a classical stochastic equation for the sources that determine the background magnetic field via this background gauge potential. So for this stochastic noise, I will call it noise, then we can assume certain statistical properties. So we will assume for simplicity that we have white noise in the spatial dependence of this background field. So it is delta correlated, and the strength of this this autocorrelation function will be parameterized by this delta function. It's a delta parameter, which is a positive quantity. So this type of white noise can be described by a functional Gaussian distribution, like this. And therefore, any observables in our system under this assumption have to be submitted to a double average. So first we will have, from the quantum field theoretical point of view, the average over quantum fluctuations that come from the generating functional of the quantum field theory. But on top of that, since the background magnetic field to this potential acts as an external parameter in the description of the dynamics, then we also have to average over the fluctuations of this external parameter. And we will average according to this distribution function. For this purpose, we formulate in the context first of QED the Lagrangian, where we have the fermions coupled to, as usual, to photons, and coupled to this classical fluctuating background field. And then we split the Lagrangian into the one which is submitted to the average of this background field, plus a fluctuating part that couples the fermions to the fluctuations linearly, right, through the current. And then how we perform such averages? Well, I mean, one needs to think that in the context of quantum field theory, all observables can be expressed in terms of correlation functions. So if we consider an endpoint, in this case, a 2K, right, point correlation function, it will be functional also of the configurations of this background field. And formally, we have to take functional derivatives with respect to the sources of the logarithm of the generating functional, then setting, of course, the sources to 0. But then under this assumption of noise in the background field, we also need to average such correlators with respect to this classical disorder. So we need to average the log offset. And then technically speaking, to average the log offset requires to express log offset in a closed form. So one way to do that is by using the so-called replica method or replica trick that goes back to the mid-80s, was proposed back then by Parisian co-workers. And it uses the following simple identity. If you take z to the n minus 1 over n, and you take the limit when n goes to 0, then this is simply by the Taylor expansion. This is log of Z. So basically, in order to perform the statistical average of log of Z, by using this identity, we perform, or we expand the phase space into n replicas of the original quantum field theory in order to generate this Z to the n. If we generate these n replicas, then each fermion field will acquire an additional index, which is the replica index, and then we have this extended quantum field theory for the n replicas. And now when we perform the statistical average, which is to take the integral, the Gaussian integral, over the fluctuations of this replicated Lagrangian in the action, then since the fluctuations couple linearly with the fermion currents, then we have a Gaussian integral that can be done exactly, analytically, and this generates a self-interaction in the fermion sector of the theory. And this self-interaction is an interaction between the vector currents, like this. But what is interesting is that this self-interaction, which is purely due to a statistical average that we perform, is proportional to a coupling constant that depends on the noise, magnetic noise autocorrelation, delta V. And it's also a contact interaction, because we assume white noise in the description of these fluctuations, so this determines a contact interaction, this delta function. So now if we commit to a given gauge choice, which is in this Landau gauge, then we can use the propagator, the Schwinger propagator in perturbation theory in order to obtain what we call the noise-dressed propagator. That means a propagator in this effective interacting theory that includes the effects of the noise via a self-energy component. So this is only the inverse of the Schwinger propagator, and this is the self-energy. And then diagrammatically, the self-energy at the lowest order in delta, first order in delta, looks like this. So we have this diagram that involves in this dashed line this contact interaction. Since it is a contact interaction, then the Schwinger phase that would go in this fermion propagator line inside the diagram will cancel because we have two identical points in space. So the phase goes to 0. So there is no contribution from the Schwinger phase inside this diagram. So we can solve this equation in the Fourier space. We can express the self-energy exactly. So you can see that it gets again parameterized in terms of this A1 and function and its derivatives. And remarkably, it has the same tensor structure as the Schwinger propagator in the constant magnetic field representation. So we can invert the Dyson equation at this particular first order in delta case and obtain an expression for the noise-dressed propagator that looks pretty much like the one we had for the propagator of a free particle in a constant magnetic field. But you may see that we get a redefinition of the momenta components, right? We have this tilde redefinition. What is this tilde here? This tilde here means that for the spatial component of Q, we introduce a factor which is nothing but the wave function renormalization factor of this interacting theory. And this will act then as refractive index for the propagation of these quasi-particles, which are dressed with the noise. So then we have quasi-particles which are dressed by noise, and it's like they are propagating in an effective magnetized medium due to this disordered fluctuating field. So we have close analytical expressions for these renormalization factors, both Z that I just described. It determines the refractive index, and also another factor, which is Z3, that acts like a charge renormalization factor here in the coupling with the sigma 3, which is basically a spin in the standard Schwinger propagator. If we plot, I mean, if we do a numerical, representation of both the refractive index, which is inverse Z, as a function of the energy scale here, we see that for large energy scales, it tends to 1. So basically, the noise has less effect over high energy components of the propagator. It affects much more the low energy components. And as you keep increasing the magnitude of the average magnetic field, again, this renormalization effect becomes stronger. Same thing can be seen here. Now the color spectrum represents the energy scale. And now we're plotting the refractive index as a function of the magnetic field. Again, the stronger the magnetic field, the stronger then the renormalization effects in this refractive index for the propagation of fermions. These calculations are numerical, but they involve all the Landau levels to this A1 function I was quoting at the beginning. So it's not an approximation in that sense. It involves all the Landau levels. If we want to do some analysis of this, of course, we can go to the standard limits, very low magnetic fields, or very strong magnetic fields where the lowest Landau level contribution will be given in close analytical form in terms of these two expressions. And in particular, you can see that for extremely large magnetic fields, then in particular, the C3 factor goes to 1/3, so it saturates in a constant, while Z will, in general, increase linearly with the magnitude of the field. Okay, so this, according to a general picture we have for the Fermi propagator. So now, what happens on the photon sector of this theory? So more recently, we computed the photon polarization diagram by using this fermion propagator, which is dressed by the noise. So it's basically following the same structure of the photon propagator, but we replaced the internal fermion lines by the noise-dressed propagators in this quasi-particle picture. We retain only linear in delta terms, consistent with the approximation we committed at the beginning. And also, in order to get a better grasp of the results, we're not pretending to be super precise here. We want to see what is the effects of noise qualitatively. So instead of using the full expression with all the Landau levels, now we're going to use, in this calculation, the lowest Landau level. And for the lowest Landau level, the propagator has the noiseless component, which is just this exponential part. It's polarized on the parallel spin sector. And a noise contribution, which is proportional to the noise autocorrelation function, which is this S1 term, where these functions, θ1, θ3, are defined by these polynomials. Of course, we have as well the spin projectors, as usual. And if we use this propagator to compute the photon polarization tensor, then it can again be split into a noise-independent part in a component which is proportional to magnetic noise. The noise-independent part reproduces well-known results that we can obtain directly from our expressions, but of course you get the typical threshold. But then the noise-dependent part, which is the second term, arises from 3 tensor structures that have to be computed separately. So these are the 3 tensor structures computed in the approximation of the lowest Landau level. These θ1, θ2, θ3 are the functions I just quoted in the previous slide. And the question then that we posed is, given this particular approximation for the photon propagator and given that we have noise, is it possible that the noise might generate a photon mass? Yeah? So in order to investigate this problem, then we need to explore what is the the pole of the polarization tensor by setting the limit p0 going to 0, p vector going to 0. Of course, the noiseless part doesn't have a pole because photons do not have mass, but the noise part will have a contribution that depends on the limit of these 3 tensor structures. And indeed, these 3 tensor structures lead to finite contributions when we take those limits. which can be calculated and computed analytically. So we have a well-defined expression in terms of the magnetic field and, of course, delta, which is what multiplies these three tensors. So when we collect all together, we have that this limit for the noise contribution is proportional to delta. It has this explicit structure that in the Dyson equation for the photon propagator, we can invert it to obtain then analytically the noise-dressed photon propagator in this effective theory. So you may see that indeed we obtain parallel and perpendicular masses for the two parallel and perpendicular sectors of the Lorentz space, but we also get an additional tensor structure here, which is basically the projection along the tensorial projection along the direction of the magnetic field, which is of course expected. And the masses that we obtain here through the poles are complex masses, because m squared is imaginary for both parallel and perpendicular components. If you have imaginary masses, that means your propagator will have then at the level of the dispersion relation a damping effect, right? So then these photons will propagate, likely the fermions will propagate in an effective magnetized medium that also is an absorptive medium, because it will damp their propagation due to this noise effect. This is what a theoretical prediction implies. So to conclude then, we have investigated this effect of magnetic noise under the assumption that the fluctuation induced by the initial conditions prior to thermalization will generate an anisotropy which is stochastic in the magnetic field that the fermions will feel. Then, as a consequence, we obtain a fermion propagator that describes quasi-particles in a magnetized medium on the fermion sector, and on the photon sector, we have this absorptive medium that generates a damping effect on the corresponding photons. So, am I done, or I have more time? 5 minutes. Okay. Yeah, I would just very quickly, because time is very short. So very quickly, a more recent work. This is more like an announcement, but it's related to the effects that noise may generate on the photon yield. So this paper is already published. I don't have enough time, unfortunately, to discuss it, but if somebody's interested, I would really be happy to discuss it, later on, along with Jorge, who's also participating in this work. Okay, so with that, I will conclude and to leave some time for questions. Thank you.
This is very interesting talk. I have a question about the physical meaning of this delta. From the formulas, I see that it has the units of inverse mass, or basically
yes, correct.
units of length.
That's correct.
So what's the interpretation of the physical meaning of this? And in the context of heavy ion collisions, what's the, I don't know, estimates you would take?
Yeah, so we have some phenomenological estimations. They are not refined because we would need more input from either from simulations or from the experimental community to refine it. But so far, our bet is that it might be related to the scale of the collision cross section that you get. I mean, this inverse length. Actually, I have some. I think I have it in the backup. I could quickly talk about this, but yeah. So this is as far as we have. Oh no, I don't have this. Yeah. Okay, so yeah, so this is the scaling analysis, right? So if we assume that the fluctuations in the field are mainly in the transfer directions, because you have all the average field is focused in the z direction, but we also have this spreading, right, in the transfer directions. So if we assume that this spreading is in the transverse plane, then we can assume that the typical length will be on the order of the square root of the scattering cross section. And if we use that, that idea and we consider, the fluctuations in these perpendicular components from simulations in the literature, we can estimate that these fluctuations in delta V go as roughly a fraction of the Python mass squared, about a half or so. And then this delta V we can parameterize in this hypothesis, like this.
Okay,
this would be a
Okay. Just a short question. I'm wondering if in the limit of strong magnetic field, your theory goes to integrable Turing model. Because you have 1 + 1 dimensional theory of fermions, contact vector-vector interaction, no propagating photons.
Right.
So it looks like it should go to Turing model in strong B. Is it true?
Actually, we have treated the model in mean field because it's an interactive model. So it's, in a sense, you can treat it similar to what you do in Lambunja and Alassini. I mean, to decouple the interaction by introducing an auxiliary boson field, and then you integrate the noise then, and then you get an effective interactive model on this auxiliary boson sector. Yeah. But then this boson is actually a vector boson because you have 3 currents, one for each current component that couples to the noise. So we solved that problem also. I'm not presenting these results here because I wanted to focus more, of course, on the novel results. But we have done that. It's published already.
Okay.
Yeah.
Thank you, Enrique. Very nice talk. I was wondering 2 things. One is that the imaginary, or rather only imaginary mass that you got doesn't break gauge symmetry, I suppose. So gauge symmetry is still respected.
Right.
Okay. And the second is that it seems that your result implies that instead of having extra photons from magnetic fields, you have less photons from magnetic fields, even though you have a V2, because you still break Lorentz invariance in one direction. So is this true? Would you be predicting a lesser yield of photons from magnetic field, fluctuating magnetic fields?
There are 2 competing effects, right? Because this polarization tensor is telling me, in principle, it's only, at the level I'm talking about, it's only the self-energy of the photon propagator. So what this is telling you is that a given photon will propagate and will get a damping, so because it's an absorptive medium, and then it will just spread for a finite, length, basically, and it extinguishes, right? But then if you interpret the photon production, which is the part of the talk I didn't have enough time to explain. But so in the photon production, we see anisotropies which arise from this noise contribution. This is what we actually see. It's not really that the rate is much decreased. The photon production rate seems to be on the same order, but we see an enhancement in the anisotropies. Again, within the calculation, we did it in the lowest Landau level, which is for very intense magnetic fields.
Let's thank Enrique again.
Thank you.
Now we have online, right? Yeah, now I have online talk. It's Maxim. Let me check. Maxim está conectado? Já está lá.
Yeah, can I start?
Hi, Maxim. Can you hear me?
Yes, I perfectly hear you. Can I start?
Okay. Welcome. Okay, so the next speaker is Maxim Chernodub. Go ahead.
Okay, thank you, Anna. Thank you very much for organizers to give me this opportunity to give this talk. I'm sorry not to be able to be present due to organization of another event. So since time is short, let me just start from very beginning and move quickly. So this talk is entitled that it's Chiral and deconfinement thermal transitions at finite quark spin polarization in lattice QHT simulations. It will be about the how the matter. Okay, so let me just start like this. So we have a general theoretical aim just to understand the effect of finite spin polarization on QCD thermodynamics It's not about rotation. It's about how a system reacts, how QCT reacts to finite spin polarization in the medium. However, this question is rather broad, large, because we can talk about polarizations of gluons or polarization of quarks. Here, I would like to ask a more focused question. So how the QCD crossover temperatures, here the confinement temperature and chiral restoration temperature, depend on quark spin potential. So the idea of quark spin potential, if you introduce it, we just polarize spins of quarks along certain axes, and this quantity doesn't produce any baryon electric or axial charges, so just spin polarization. Concretely, in this short talk, I will discuss a very concrete question. We would like to introduce a polarized quark medium in the system in quark-gluon plasma, and then with the help of certain spin potential, which is this one, quantity kappa, and then we would like to understand how temperatures, pseudocritical temperatures of crossover transition, will change with this chemical potential. So idea is basically the same or similar as the behavior of the critical temperatures or pseudocritical temperatures of the crossover transitions in the presence of the baryonic chemical potentials at finite baryonic density. And this work, this talk is based on this published work with Victor Braguda and Artem Royenko, just made this year. So the motivation is very simple, it just comes by rotation. Basically, I shouldn't explain in this audience that we know that there is this very famous experiment when the most vortical fluid was ever first created in a central heavy-ion collisions at star. It has a very tremendous angular velocity, a global vorticity, and vorticity, we know it polarizes spins of quarks and polarizes all internal momenta, angular and also spin momenta. And polarization goes normally, we observe it experimentally in terms of produced hadrons because they acquire spin from polarized quarks. And this is basically the Barnett effect, which is right now written in the quark level. So if we take some unpolarized medium containing, say, for example, ferromagnetic particles and rotate them, then particles will try to elongate along the axis of rotation, so they get polarized, and this is seen as magnetization because those particles has intrinsic magnetic moment. That's famous paper by Barnett, magnetization by rotation, more than 100 years ago. So right now, we would like to ask the question, okay, we don't have any rotation. Imagine that we have somehow QGP with non-zero spin density of quarks generated by some effects, maybe by rotation, but they remain, rotation stopped, for example, or whatever passed, but we have just medium with some spin polarization, and we would like to understand what will be effect on thermodynamics of the system. For us, simplest way, we just consider uniform time-independent spin density, so like we do usually with magnetic field. Normally, of course, I know about Gergo talk, where different profiles are considered, but in the early stages, we consider just uniform spin density and assume that all charge densities are vanishing. So basically, it's like a vacuum, so where we have no charges, but contrary to the vacuum, we have spin polarization. So for example, here the simplest configuration which we can imagine. So we have U quark, anti-U quark, D quark, and anti-D quark, which have spin polarized along the some certain axis. So this is the axis, and spins add up, but all the charges in this case is isospin and baryonic charge, electric charge, they cancel each other. So therefore, it's basically we make all charges vanishing again as in vacuum. But it's not really vacuum because it's actually thermal medium. So we work actually with a quark-gluon plasma, which is polarized. So, and then the question is how we introduce spin of quarks. Okay, we have various questions here. The simplest way is to introduce using relativistic spin matrix, so using canonical formulation. So we take this famous combination of the Dirac matrices, introduce it in the Lagrangian, this is just shift to the Lagrangian, and multiply it by Legendre factor, which is finite, some certain quantity which carries various special indices, in this case 3 indices, which represents our how actually spin is polarized in the medium. So if you, for example, take this particular choice of this particular form, we can characterize this quantity just by one number, which is a component of the spin potential, which says that in our laboratory reference frame, here we have spin polarization along the third axis. And this quantity, those quantities are very much important in spin hydrodynamics. Here I quote some references on the review references and working references on the subject. So it's very, very known. And of course, we have a difficulty here because we have so-called pseudo-gauge symmetry, which doesn't allow us locally to define the operator of spin polarization. But we have some examples. Here I would like to quote some papers by Matteo, the paper by Matteo and Andrea about the fact that in attracting theories, depending on the form of interaction, the system somehow selects the correct spin. So our idea is the following. So we just put this canonical operator and see what happens with gluons in this particular case. So the idea is that we introduce this spin polarization, as I said, along the static in laboratory frame, along the third axis. Then one should immediately notice that it's kind of very similar to rotation. If you just apply rotation to the system and look to Lagrangian in the rotating reference frame, you will see exactly this term, which corresponds to spin polarization, basically to the Barnett effect, plus orbital rotation, orbital term. This orbital term is actually dangerous because it leads to causality problems if you consider a system too big. But in our case, we can consider a system easily in thermal equilibrium because we don't have this term. So no orbital rotation, no problem at all. However, one should mention here that spin is not conserved quantity. Therefore, this mu sigma should not be called as chemical potential. It's just spin potential, and that's all. So in some sense, it plays the role similar to baryon density, so similar baryon chemical potential, baryon density, but we should take into account that this quantity is not conserved. Still, we can introduce it and look what happens, whether the system would somehow adopt it and reacted to it accordingly. Let's see. So this work is done in first principle simulations. So we just should introduce this quark spin density term. We work as NF equal to 2 QCD, so it means that we consider 2 light quarks, U and D. We don't consider any other quarks like S quark. It's the simplest formulation. Then we have to note, to make the simulations, we need to make a weak rotation to Euclidean spacetime. It means that immediately we get a sign problem. So the system becomes imaginary in Euclidean spacetime. So therefore, we need to introduce an imaginary spin potential. Therefore, in that case, if you introduce it, then the Euclidean fermionic action becomes real valued, but we can make calculations at imaginary imaginary spin potential, and then continue back to the real world again and check what's going on there. So in lattice action, we use, just for experts who are in the audience, we used a very good action. Okay, one of the good actions, it's normalization group improved Iwasaki lattice action for gluons, and also Clover improved Wilson fermions for fermions actually. So that reduces the lattice artifacts when we approach continuum limit. So we consider 2 types of observables. They are natural. One of them is the confinement observable, which is Polyakov loop and its susceptibility. Another one observable is for chiral symmetry breaking. That's susceptibility of the chiral condensate. We will consider the connected part of this quantity. And then, of course, since we work with imaginary chemical, spin potential. I always say chemical automatically, but it should be said spin without chemical. So we're working with a spin potential, imaginary type spin potential, then we should say that just from general point of view, we can imagine that at pseudo-critical temperature of the crossover transition should be quadratic in the first order. There should be quadratic function of the this spin potential, and therefore analytical continuation is very simple. So for example, if temperature increases with some factor kappa, then when we pass to the real spin potential, then this kappa should be inverted. Basically, we should have sign minus here. That's in the very same way as happens with the baryonic chemical potential. So our quantity of interest is the pseudo-critical temperature of the crossover transitions. And I would like to say that we consider 2 transitions. We consider both confinement and chiral transitions in search of eventual splitting of them. Because in fact, what's going on here is that we introduce polarization for quarks, and somehow this polarization can be transferred for gluons and affect gluons. And in principle, since the primary quantity is quark, we can imagine that in principle, those 2 transitions may split, for example, or change their order. So that's important. So our strategy is rather standard. So we consider many temperature points in the crossover region around pseudocritical temperature. We consider rather heavy meson masses, but then we extrapolate it to the physical mass value. So it's just physical mass value corresponds to this ratio between pseudoscalar and vector mesons. In this case, it's pi meson and rho meson respectively. We also check how big are these effects of our ultraviolet cutoff are. So therefore, we vary imaginary time. And also we check how close we are to thermodynamic limit, changing spatial extensions of our lattice. One important point is that we don't normalize susceptibilities, which we use to probe the transition, because we believe, also it's very well known, and also it was mentioned in the talks here by Gergo and Eduardo, that in fact we have some normalization, but we noticed that we carefully checked it, and we noticed that it does not have the effect on this temperature ratio because it shifts both temperatures in exactly the same way. So we hope that this ratio, pretty sure that this ratio does not change by those effects. So, and then first of all, I would like just basically come to the end of the talk, saying that we should first notice the qualitative effect of polarization of quarks, of spin-off quarks, on gluons. So here I consider the Polyakov loop. It has not been used for determination of temperature, but just for qualitatively to show the effect. So we consider some specific mass ratio, some specific temperature extension, and then we vary the chemical potential, sorry, spin potential, as a function of just spin potential. We just increase it from 0 to 0.5 squared values of, and we vary it, and we see immediately that as we increase the spin potential, then the temperature, the value of the Polyakov loop decreases. So it becomes smaller as we increase spin potential. That means that the finite imaginary spin density favors confinement and increases crossover temperature. So if we believe in analytical continuation, and we do believe it, so that means that real values, so real spin density, favors deconfinement and lowers the critical temperature. So that's first thing which we get from this picture. But then let's make it quantitative because we like numbers. So here I flash briefly transparencies, what we did. We have many pictures, but these are representative ones. For example, for confinement, we measured susceptibilities of Polyakov loop at various string spin potentials here, just increasing them. For example, we see that the temperature moves to the right, so it increases with imaginary spin potential. The same tendency works also for chiral symmetry, so we see some increase to the right. Also, we see some change in the kind of strength of the transition in the chiral sector. So, but it's really seen here. And then what we do next, we of course we have those points here. We fitted them with the Gaussians, and then next point is just to make extrapolation. Or to look how, for example, it looks really, whether we have quadratic behavior, parabolic behavior as the pseudocritical temperatures as the function of the imaginary spin potential. So here we see imaginary spin potential squared, and here is pseudocritical temperature of the transition, and we see almost perfect lines here for all possible lattice extensions. You see that it's just for lighter quark masses and for heavier quark masses, those behaviors are approximately the same. So we see that we have really parabolic dependence. And then the next step of lattice, of course, we need to extrapolate those curvatures. We need to extrapolate them to physical value. And here we plot the curvatures of the transitions. So we measure them. We plot the curvatures of the transitions as the function of meson mass squared. So let me repeat that curvature of the transition is just this coefficient in front of the parabolic dependence of the pseudocritical temperature as the function of spin potential. So we make those fits. And for each curvature, we plot each curvature as a function of meson mass ratio squared, and just extrapolate those curvatures to the physical value. And it's interesting to see that the confinement and chiral transitions, they basically a little bit different and finite masses, but when masses go to light physical limit, we see that those bonds, they coincide. So these are extrapolations, and we see that those transitions, they are basically the same. And here, for example, those curvatures, if you measure them, let me just jump to next transparency. So those curvatures, they predict that for real spin potential, we should have this behavior. So we should have quadratic behavior at small spin potentials with those curvatures which are positive. Moreover, they are positive and they are very similar. So they are basically the same within error bars. So we conclude that we don't have split of the transitions, neither of confinement nor or chiral transitions. And in fact, it's of course interesting to compare those spin curvatures to the very well measured other parameters. Here, for example, I took the curvature of the finite baronic density. So it has been measured right now with a good precision in more or less realistic, actually more realistic than our case, QCD with 2 light quarks and 1 heavier quark. So if you translate it to the quark chemical potentials, then we get that the curvature of the baronic transition would correspond to 0.12 approximately. In our case, we have 0.06. So we are approximately the same, in the same range of effect. And I would like to say that this behavior can be captured in effective infrared model. We had a talk on Monday by Pracheta Sinha about the fact that one can find this behavior in linear sigma model, and moreover, one can extrapolate it to higher higher spin potentials. So the spin potential, in our case, we consider only behavior very close to the zero spin potential, to an unpolarized case. But those models allow us to extrapolate it further and predict, for example, existence of some critical endpoints and the first order phase transition as well, which we here cannot capture so far. So now I'm coming to conclusions. I hope that I'm in time. So the conclusions are that we applied first principle lattice simulations in 2 flavor lattice QCD, and we show that the confinement and chiral crossover temperatures, they drop together with increase of canonical quark spin density. I say canonical because we introduce it using canonical spin operator. So this is qualitative behavior, and the curvature of this transition for both transitions, actually they coincide and they are overlapping, and they are given by these dimensionless numbers. And the interesting thing that we have no problem with pseudo gauge symmetry. So it looks like with the it's like confirming the work of Matteo Bozzegoli and Andrea Palermo that indeed the system somehow chooses how to distribute spin which we introduce with this non-pseudo gauge invariant quantity to the system. And the magnitude of the spin curvature is comparable with what we expect at the finite baryon density. And we don't have any split again. And yes, and despite, that's what I said, despite the density of quarks and conserved quantity, the QCD thermodynamics is sensitive to the quark spin polarization. Okay, I'm finished.
Thank you very much. Maxim, can you hear me?
Yes, I hear you. Yes,
I have
yes.
several hands raised here.
Hey, Maxim. Sorry not to see you here.
Hi, Georgia.
This is a really interesting approach. So this is this conference and another talk I makes the paper. So spin is not conserved, but angular momentum is conserved. And however, sort of angular momentum in an equilibrium is vorticity. Vorticity is sort of non-extensive. Spin density is intensive. Angular vorticity is neither extensive nor intensive, and also spin causality forbids angular momentum and spin to be perfectly in equilibrium all the time in a dynamical system, unless it's in global equilibrium. This is sort of a result that you can derive. So my question is, if you compare your earlier rotating on the lattice results with spin density results so that angular momentum is the same, how different are they?
You see, we don't know how to introduce here angular momentum. Actually, it would be nice to check what angular momentum.
You did rotating reference frames.
Yeah, sorry?
You had the rotating reference frames, so you know what the angular momentum in the rotating reference frame is.
No. That's actually this point. You see, we don't have orbital rotation. Let me just make it
No,
dynamic.
but in the past you did orbital rotation.
Yes.
Yeah.
So in this case, we have actually thermodynamically nice system. We can make, indeed, extensive, we can make it as big as possible. But, we don't know what to compare with. In fact, we will, of course, we will try to check it later. We would like to, for example, to check how spins are polarized in rotating real system and then compare, for example, to this polarization. But, but the results of this polarization, but that would require hard work because you see that there are some problems here. So because, for example, we would like to measure the spin density, and exactly, that's what the first question to answer, but it would be difficult. We need to make probably some renormalization, as I said. And from talks of Gergo, we know that this normalization can be done with very big care. And also with Pracheta, this what I cited here, with her talk, we really paid really big attention to normalization. So that's actually, I would like to say that's difficult stuff. So, but this can be done, this can be compared. Thank you for the question. We will try to think about this. How to compare kind of non-rotating system which looks like rotating, whether we have some rotation of gluons. But what I expect that we kind of pass some of the our spin polarization of quarks to spin polarization of gluons, and it should somehow be related to this proton spin puzzle in some way, maybe in this thermodynamic way. But we don't know how to. We are in infancy. We don't know how to correctly measure it, so it's a little bit complicated right now, just due to artifacts.
Okay, thank you, Maxim. So Igor.
Hi, Maxim. Sorry not to see you here locally, but very nice talk. I like the talk and the results seem interesting, but I'm wondering whether you are really considering spin polarization. Introducing this quantity has nothing to do with the spin, and you, one of many people who worked in Dirac semimetals, know that this kind of operator introduces a shift between the origins of the left-handed, right-handed particles in the fermion sector, and pretty much it has nothing to do with the spin polarization. You're just shifting left-handed in one direction, in KZ direction, right-handed in the other, and that's it. And in this case, of course, chiral symmetry becomes much easier to break because you are separating them spatially in momentum space, and they don't want to pair. And that's all it is, it seems.
Okay, so I know that it's just this kind of this is a spin shift in this between those Weil cones that we know indeed from Weil metals, but probably this question can be addressed to those people and to those people whether this is spin operator or not.
They also should consider that that is not spin operator.
To me, it's a little bit of religion because of this pseudo-gauge symmetry. Because you know that if you consider, for example, the expectation values of the total angular momentum in the rotating reference frame, we will clearly see this part, which corresponds to integer valued orbital momentum, and this part, which corresponds to half integer valued spin momentum. So for us, this quantity is better to introduce, kind of it's natural to introduce the spin, but I have reservation here. Indeed, we have this pseudo-gauge symmetry. And if one can come back to the beginning of our work, we can ask ourselves what kind of spin should be introduced, how we can probe the spin, how we can polarize it. And this is simplest quantity, this Pullman approach, how we can introduce something like spin. So maybe in reality, maybe it's like introducing, like measuring some, say, non-gauge invariant quantities in gauge invariant system. The system averages over all possible definitions and gives you something which is physical, which is gauge invariant. So that's my interpretation. But indeed, you're right that it can be interpreted like a Weil splitting in the Weil metals. That's we know those works. We know that in magnetic field they will be shifted, and I know your works very well in this case. But this is Pullman approach in lattice gauge theory, and I think that we are in agreement with the, I would say, psychology or the determination of other people who are doing this work. But conceptual problems, yes, exist. I totally agree.
Yeah, a quick question by Gergo and a quick answer by Maxim, please.
Yeah. Hi, Maxim. It was a great talk. I just wanted to mention that in the case of the magnetic field, there is also this separation of the response into orbital angular momentum and spin, which we derived, and I would really like to, which is very similar to what you show here, and I would really like to discuss with you how the similarities between these two responses. So I think we could discuss that. And a very quick question is, when you introduce the spin potential on the lattice, you said that you don't want to worry about renormalization, and I understand that, but does this term induce an additive divergence in your free energy, and could you also introduce it with an exponential form? Would that help or not?
Very good question. That's why we have not measured free energy yet. we measured only, we were very careful. I expected this question from you. We were very careful. We measured only susceptibilities. Because in free energy, we expect that we will have this big contribution coming from, ultraviolet divergent contribution coming from the presence of the kind of spin potential, I want to say chemical potential, but it's not chemical potential, associated with a non-normalized quantity. We do expect those problems, but in susceptibilities, we don't have them. That's why we were very careful enough to consider only this ratio. But I agree with you, problems do exist. That's why we could not measure right now the density carefully. And we also planning to measure equation of state. So basically free energy, which you mentioned, but we expect there to have some issues. Yeah.
Okay, thank you, Maxim. Let us thank
Thank you.
Maxim again.
Thank you. Thank you. Thank you very much.
Okay, now we have Jinfeng.
Hello, hello.
Hello, ready?
Yeah, let me, I guess, share my screen. Trying to look for my. Wait, it's wrong here. Okay, so that's the. Okay, sorry. Okay, so do you see my screen?
Yes, but it's not full screen.
Okay, yeah, I'm gonna get it full screen. How about now?
Oh, yeah, it's perfect now. Okay.
Okay.
Please.
Okay, thank you. Let me first thank the organizers for this great opportunity to discuss some of our recent updates. Also, I'm sorry for not being able to come and see many friends here. Hopefully, the phase that I'm going to talk about will be interesting. So I think for the audience of this conference, I guess we don't need too much of an introduction. So I just want to kind of repeat one point I made many times, that we have spent some over 3-4 decades to study the energy momentum transport in perfect fluid or nearly perfect fluid. It has been only recently that people start to pay attention to the spin degree of freedom in this fluid. So I think that's a good thing, because we can expect another maybe several decades of understanding it. And you can see that from the discussion, this workshop, that many questions remain to be answered. I think, so how to, probe spin degree of freedom? I think we had a lot of wisdom from, for example, condensed matter or atomic physics, that we know how to play with spin. For particle spin, like the quark spin, you can think of a variety of ways of playing with them. Like you can think about chirality, which is the correlation between momentum and spin, or you can probe spin through magnetic field, which leads to magnetic polarization. And also you can use a global rotation, vorticity, to polarize the spin. And fortunately, we have these conditions available in a heavy ion collision environment. So that's very good. That leads to many, very interesting transport phenomena, and we can measure them in those experiments. Okay, so in this talk, I'm going to focus mostly on the heavy ion aspect, like some of these effects, and how we find them in heavy ion collisions. I will start first with the current magnetic effect. Again, I don't think you need any introduction. I think everybody is familiar with this. And if you have questions, please just ask Dima, since Dima is there. So I just want to briefly say that this is really an interesting phenomenon. It's a macroscopic manifestation of chiral anomaly and gauge field topology. And also it has been observed in systems like Dirac and Weyl metals. So for us, the key question here at stake is that can we observe it in heavy ion collisions? So that's what I'm going to focus on now. Now, have we seen the CME? So this is a question that has been repeated, asked, believed to be answered, and then asked again, and so on, since the first measurement of star in 2009. So a lot of effort has been made, at both RIG and RGC. Many colliding systems being measured. It proved to be a difficult search because
sorry, the slides are not passing.
Sorry?
So we see only the first slide.
Oh, really? Okay. Let me see what happened. Okay, so let me. So let's see. How about now?
Oh, yes, but it's not full screen.
Okay, so let me again go full screen.
But can you test if or if it's stuck in this?
This is weird. Let me see.
I mean, now we saw your third slide, but maybe you could test if it's passing now.
Okay, let me try again.
No, first slide.
Never seen this issue.
I mean, you can leave it like that. I mean, the screen is large enough so we can see. I think you
Okay,
can
so let
leave
me
it like
see
that.
if I can. Okay,
Not
so
full screen.
I don't know if it had to do with the fact that I pinned this one. I think that could be a reason.
Isn't it view on the top left? Can you choose view full screen or?
Okay. Okay, so there is some issue here. Let me try to stop sharing and redo it again. Okay. Okay, this I don't understand what's going on here. Maybe I just make it bigger. That work?
Yeah, it's fine. It's fine.
Okay, so
Yeah.
and you're suggesting that's just slide only. Okay, so that work better? Should I continue?
It's less.
Okay, all right.
Yeah,
okay.
That's good. Oh
Okay.
yeah, it's working. Okay.
Okay, so I'm here. I think I just want to say that we've come a long way in fighting the background. So the main issue I think is here that what we measure, the observable, the so-called gamma correlator, contains both a possible CME contribution and a background contribution. And I think this little bar here kind of indicates that it will have a relatively small signal with a large background. All of this background, the majority of that background is what we would call the flow-driven background. It's due to effect like what we call the local charge conservation or resonance decay, and then there could be also some non-flow contribution. The good news is that I think through a lot of effort by experimentalists and also theorists, we have understood this much better. I think especially for the flow-driven, this dominant part, we understand much better now. So we're getting very, very close to be able to really kind of extract the signal out of the measurement. So this is the recent, I think, relatively recent review that we wrote last year together with Dima and also Priswish. So in this article, we try to put together all different measurements of CME signals from all these different collaborations. You can see that, of course, right now at that point, until we wrote this review, there were very, very good indications of all these signals, especially in the RIC regime, in the 200 GeV or 27 GeV. We do see some finite signal, and of course the error bars are still large. I want to particularly make some comment about the isobar because that was something that caused a lot of confusion. So in terms of isobars, so the original idea was that you have two colliding systems that are really close or really almost identical in terms of background, or they should have different signal due to different magnetic field strengths. And that original idea didn't work out exactly because the backgrounds are actually not identical. They have about a few percent of difference. But if you're able to carefully take that into account, you can still make a comparison or contrast between these two. So that's what we did after the isobar blind analysis, when we were able to see all the data or measurement for the ruthenium zirconium. So in this paper with Dima and Shude, we carefully took into account this difference in the background through the AVFD simulation and then also the signals. So our conclusion is that based on that comparison, you actually have a signal on the level of like 6.8. And that, I think, I want to point out that after the blind analysis, STAR published 2 papers to follow up on that. after unblinding. So these are their latest words on the isobars. They have been able to put an upper limit, which is certainly leave plenty of room for signal, and also that upper limit is consistent with the extraction based on our simulation and comparison with data. Okay, so that's for the isobar. I think the latest exciting news from STAR is, I think, the measurements from beam-magic scan 2. I believe probably Huang and others have discussed this at the conference. This data, I think some of these were first shown at Quark Matters 23, and then I think was formally released just probably last month in these two papers from STAR. To cut a long story short, I'm sure our experimental friend will discuss this in detail. I just want to point out that in this 10 to 20 GeV range, there are several points with about 3 sigma signal. So that's a great news. So what we want to do, on the theory side, is we want to understand what these data points mean. I think this is really a magnificent result. It's probably some of the most important results in the last couple of years. So I think we really want to understand what they mean from a theoretical point of view, from the view of finding CME. Okay, so I think that's the project we started, since the Quark Matter 23. So based on this event-by-event anomalous viscous fluid dynamics, this was the framework that we developed for quantitatively simulating both the CME transport and the background in heavy-ion environment. So the details are in these publications. So what we did new here is that we want to upgrade this for the BS energy, because there are some differences between the 200 GeV and for example, 19.6 GeV. So we made a lot, like changes or upgrades so that it can be suited for simulating the bulk evolution at this kind of energy. For now, we're focusing on 19.6 GeV. We did calibration with bulk data, meaning that you want your simulation to accurate or relatively accurate describe your bulk evolution. That included, for example, some indicators like multiplicity, V2, net proton, and so on. So they're all very good. And then we want to systematically scan the key parameters for ferromagnetic transport. We actually, so that what that means, there are 3 key parameters here. First of all, there's the magnetic field lifetime. This is one of the most uncertain quantity, okay? I'm sure there are discussions on the dynamical magnetic field evolution at this conference, but the bottom line is that we are not very sure about magnetic field lifetime. And then of course there's the initial condition for the axial charge that due to topological fluctuation, you get some non-zero M5 to start with. And then there is a background parameter, which is called local charge conservation parameter. So that basically controls the strength of this dominant background, local charge conservation. So what we did this time is different from what was done before by us or by anyone else. Namely, we decided that we no longer assume any magnetic field lifetime. We treat these 3 all as free parameters. So that's a big parameter space. And then we choose values for this parameter in over a wide and reasonable range. For each choice of the parameter, we performed about 1 million event-by-event simulations. Okay, so that means we're scanning all this space. We're not trying to assume anything. For each choice of your, magnetic field lifetime, axial charge, and your background strength, you calculate your inclusive gamma and delta. And this is the other thing that we decided to do this time, that we don't artificially separate a background contribution or a signal contribution. We just compute the inclusive gamma and delta for any given parameter point. So that, of course, you can see this is a huge amount of simulation. So you are not able to exhaust this, parameter space. Fortunately, this is not a new problem. Actually, it's an old problem for many, scientific research. Even in the heavy-ion field, I think starting 10 or so years ago, people started to realize that if you want to do quantitative extraction like a Bayesian, you have to use a Gaussian processor emulator. So that means that you scan a good part of your phase or your parameter space, and then you use the Gaussian emulator to fill in the other point. It's like interpolation, that's it, plain simple. And finally, then you can use the experimental data for your gamma and delta and use advanced statistics tools like Bayesian or neural networks to compare, and then you go reverse from measured gamma and delta to infer what are possible values of your tau B, M5, and FLCC. So again, the major advantage this time, which is very different from before, is that we don't make any more assumption about the B field lifetime. We don't separate the background signal, in our calculations. We just calculate inclusive gamma and delta. It's almost like experimental measurement. Okay, with that, so this the result is gonna we're finalizing, and the paper is in preparation. But you can see we use several methods to that included the sequential Bayesian inference and inverse neural network, to try to go from data back to parameters. So this you can see we tried several different approaches, and they're all giving you very robust and consistent results. Basically, you have a magnetic field lifetime about 4 Fermi. That's what data tells you what you want. And interestingly, you can see the LCC parameter is very, very sharp at peak. So we look up and down, left and right. We found that this is a really, really robust thing that we saw. Namely, the data is telling you you need about this amount of local charge conservation. And it's very robust. And then, of course, for N5 and tau B, this is N5. You can see it's a little broader, tau B distribution a little broader, but still they have a very, very clear preference for a finite value of tau B about around 4 point something Fermi. And N5 over entropy is about 8%. Okay, so these are giving you really robust extraction, and it's really just data driven because you don't make assumption about what's going on. You just say, okay, I'm going to throw in all my physics going on here. That means you're throwing in your carrier magnetic transport and background, and then you calculate gamma delta, and then use the experiment data to tell you what you need. And I think I think we are really excited about this result. So I think this is, I understand from experimental side what experimentalists do is that they try to use, for example, even a shape method to separate the background from this inclusive gamma, and then they get a finite signal. Okay, what we do is that we're taking inclusive gamma and delta, we're putting all the physics in, and the data is telling us that you need carrier magnetic transport here. Of course, there's a dominance of background, which is very clear, but then there is also a very, very strong and robust indication that there need to be carrier magnetic transport if you want to describe those gamma and delta. Okay. All right. So that finished my first part, and my second part is about the initial conditions for angular momentum. I think this is another topic that probably have been discussed a lot at this conference. I'm going to be quick because I don't need all this, introduction. Basically, your global angular momentum from the initial colliding system caused a spin polarization of your microscopic particles like quarks, and then that can be measured. I think in heavy ion collision, we happen to have that kind of angular momentum. It's pretty huge. I think a number of people here made early contribution to this idea of angular momentum in heavy ion collisions. What would interesting question, of course, here is that how that evolved, how this phenomenon evolved with beam energy. If you look at this simple estimate formula, you would simply say, okay, angular momentum is going to become bigger and bigger with beam energy. So naively would say, okay, that phenomenon is probably going to be more important at high energy. So I'm only focusing on the global spin polarization, okay, not local spin polarization or spin alignment. Okay, so about almost some 10 years ago, so we did some simulations. One thing we found as a surprise that the vorticity that at 10 GeV range is much bigger than vorticity at 100 GeV range for a number of reasons, which I'll come to later. But the short thing is that, if you want to look for this kind of phenomena associated with angular momentum, you want to go to no energy domain. And that is exactly what was found by Starr later in their Nature paper. After that paper from Starr, we continue to ask what happens if you push it down to even lower energy, like order 1 GeV collision. And our conclusion was that it will turn around and then the polarization will drop, because simply the angular momentum is becoming smaller and smaller and eventually vanish. And then there came this very surprising measurement. So I think there are a few points on this, a few GeV range, especially there's the star fixed target and also a hardest point. And they both are kind of continuing this, strong rise of the polarization signal. So the question, of course, obviously, is, can we understand this? Can we understand this in particular? Can we understand this as a global spin polarization induced by global angular momentum? So to understand or to answer this question, you want to understand how much angular momentum are deposited in the initial collision. And that really has to do with the nuclear stopping, because if you think about it, how you get that angular momentum into the fireball. Of course, the initial angular momentum is carried by the beam nuclei. But then after collision, a lot will fly away because there are many spectators. So what will remain in your fireball is those nucleons or wounded nucleons that are being stopped at mid-rapidity. So that is controlled essentially by the rapidity loss in the initial collision. So you can use so you say you have nucleon NA from left and B from right, and they collide with the initial beam rapidity. After that, they each lose some rapidity. Okay, you can quantify this by a rapidity loss parameter E. What control this? Well, of course, ultimately the microscopic dynamics interactions control this, but there are important constraints that are the global constraint of the conservation laws, like the momentum conservation and the energy conservation. So you can use those conservation laws together with this parameter E to actually calibrate or quantify how much rapidity you lose. So after collision, right after collision, different spots on the overlapping zone in the collision, they are going to lose different amount of rapidity. And then at each collision locally, the fluctuation will give you additional spread out along rapidity. In other words, when you start this collision, both beam particles, they have, let's say beam nucleon, they have the same rapidity values, okay, +5 or -5, okay. After that collision, they're going to spread out in their rapidity. Okay? So that's the rapidity spread out. So I use this little picture to kind of give you an intuitive idea. So the before collision, these are the beam particles. They have all the same beam rapidity. So this is the rapidity, the x-axis, the horizontal axis. The vertical axis is indicating spatial position x. This is important because the momentum z and spatial x together give you angular momentum in j in the y direction. Okay. So this is the before collision. Right after collision, what I call a global plot picture. You can see all these green particles moving to the right. They get they lost some rapidity, so they move in the smaller rapidity region, and then they get more spread out due to the fluctuation of the collision. Why the middle circle is bigger than the other? Because in the middle part, your nucleus is thicker. Okay, think about your integrating over z. Okay, so right after collision, you can see on the left the same thing happens. So you can see you get a non-trivial distribution in the rapidity right after the collision. Okay, that's essentially the nucleon stopping, and that is also important for you to compute the angular momentum distribution. Okay, so I'm almost there. So you can see these are some examples with different parameters of fluctuation and that rapidity loss parameter. You get net baryon distribution across rapidity, and you get a corresponding angular momentum distribution across rapidity. That's a good thing because we have parameters that we don't control, and you can use the net proton, measure that proton to calibrate how much baryons are stopped in the middle rapidity, and using that you can basically fix your model parameter. So once you have done that, we can look at angular momentum. This is what is interesting to us. Okay, for example, you can count how much angular momentum is stopped in the middle rapidity region. Okay, that means so what it means is that after you get this picture, you count how many nucleons are stopped in the middle, and then you compute their contribution to the angular momentum. So that's what we get. You can see we did calculation from as low as 2 GeV to as high as 500 GeV. It's actually not monotonic. It goes up and then comes back down. So I have another plot here. You can see in this plot, this is even more clear. So you can see, first of all, this lat baryon number, you stop in the middle rapidity, it quickly drops down, which we all understand. Okay, when you go to high energy collision, you have almost no baryon. Okay, and the reason is simple. At high energy, your nucleons start with a very large beam rapidity. It's very hard to stop them into the middle. Okay, and then this line is the angular moment divided by 10. Okay, just to put them on the same plot. So you can see the angular moment initially increased rapidly because when you have more beam energy, you get more momentum and more angular momentum. Then it starts to level off and eventually drop down. That drop down again is driven by that baryon stopping because you don't have a lot of nucleon in the middle rapidity. Then you don't get that angular momentum. Okay, so this picture is also well understood. You can but one thing I want to point out is that the angular momentum keep increasing and level off, and this behavior, if you normalize it with the net baryon, that's how it looks like. It keeps growing, but of course that's not a good way of normalizing your angular momentum. You want to kind of ask how much initial angular momentum I have per particle. Okay, so one way to give you a proxy for that is that you can divide this angular momentum by the measured charge multiplicity at those different energies. So this is the plot that I'm showing here. You can use either the rapidity or pseudo rapidity, depending on what data you look up. But the behavior is the same. Basically, you have a peak around 5 GeV. This is due to a competition of your increase in z momentum, therefore increase in total angular momentum, and a decrease in the stopping of nucleon in the mid rapidity. So that two competing factors give you a peak, very strong peak around 5 GeV. So the key message is that I think angular momentum driven phenomena is unlikely to keep increasing toward extremely low energy. Okay, so that's my personal take. I think so. Of course, once you have this unique condition, you can ask what can you do with it? Well, with all these unique conditions, in principle, you can use that for a spin hydrodynamic simulation, right? Hydrodynamic simulation need the initial condition, and then you need also the hydrodynamic equation for angular momentum. This is another area I'm sure there are a lot of discussion at this conference about. Namely hydrodynamics of angular momentum. I think some of you already mentioned that, for example, there are key issues like how you separate spin out of angular momentum and so on. There are many works, in this area. We also had some recent paper a couple years ago. Our kind of main point here is that if you have hydrodynamics with large angular momentum, you shouldn't treat the angular momentum as the first order gradient term. So, and also we don't want to separate spin part. So there are, interesting questions that one need to explore. So that's what we did in there. We find, for example, a few new, angular momentum transport coefficient that control how your angular moment diffuse in your fluid. But I think this is the area I think that still need a lot of discussion and future development. So I think I'll just stop here. I probably just skip reading this. Thank you.
Thank you very much, Jinfeng. So we have time for only one question. We have many.
Hey, Jinfeng. Yeah, thank you for a very nice presentation. I have a technical question about your model, and especially for the first part, where you have this N5 and also local charge conservation. Can you compare the correlation length in rapidity for those two effects? And do you have anything like that? Say how
correlation length, you mean?
Two particles would be correlated to each of those effects.
You're talking about this angular momentum?
No.
No?
For CME, just at the very beginning, you gave, this one. So you have the second and third parameter, N5 and FLCC, which describes the chiral magnetic effect, basically, and your background. I'm just asking about how you would compare the correlation length in rapidity for those two effects. If you have any, I don't know how exactly you introduced, but.
Because we are really just focused on the calculation of the mid rapidity. So you're saying that, like how this change with rapidity. Is that what you want to know?
Yeah. For example, local charge conservation. Two particles are correlated in rapidity, but they are not correlated. The correlation length is rather small, say around 1 unit. I just want similar for your chirality. It would be also correlated.
I see. Okay. So that's something I think we certainly can try to extract from the for the simulation. Yes. So, but we haven't looked at it. So you're saying that let's say two charged particles, it's like sort of plus minus correlation across rapidity, right?
Yeah.
Okay. Yeah. We can look at that. Yeah.
Okay. Thank you.
So we're a bit late in the schedule, but Jinfeng will have discussion session. I guess that for people in Europe it's a bit late, but maybe for you it's doable to be here. It will be 4:30 Brazilian time. I'll send you all the details. So I think if you can be present, you can keep with the questions because there are several.
Sure, yeah.
So let us thank Jinfeng again.
Thank you.
Thank you. So now we have coffee break, but before coffee break, we'll take the picture of the event.
Right outside, on the way to the coffee break, we all stop.